Okay, let's start. From last lecture, we have learned what is the vector equation. From now on, we will learn what is the matrix equation. What is the matrix equation Ax equals B? Okay, here is the definition. If matrix A is an n by n matrix with a column A1, AN, A1 through the AN, what does that mean? A is the represent like A1 through the blah 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 through the AN, looks like this. And then if there is some kind of vector in the of n, then the product of the a and x, denoted ax, is the linear combination of the column of a using the corresponding entries in a vector x as a weight. What does that mean? It's really wrong, right? But this statement just represent in here. Okay, so let's represent the a multiply x as a like this. So this is a matrix A. So if the matrix A, size of matrix A is the m by n, then what is the size of this column vector? What is that? N by 1, right? The size of this one is also n by 1. N by 1, right? So this is the columns of the matrix A. Then this is the vector. Okay? So each entry x1, x2 through the xn is just the scalar value, right? And then this x1 scalar value and this matrix A just can be represented like x1 times vector a1 plus x2 times vector a2 plus xn times an, like this. So what does that mean? We can represent the this ax as the multiplication of this one and this one like this one and this one like this one and this one like this, right? So what does that mean? This a times x will be the linear combination of the columns a1, a2, an with this weight value x1, x2 through the xn, right? So this is the definition of the a times x. Okay, so here are one more things. Okay, let's say the size of the matrix A is the m by n. Then what was the size of this vector? Was the n by 1, right? Then what is the size of the output? What is the size of the right hand side? What? Because the size of the A1 was m1, right? And this is scalar value. So the size of this one should be m by 1, right? So what does that mean? So to compute the AX, the number of columns, in this case n, number of column is equal to the number of entry in X. In this case, n, like here, like this. So what does that mean? Okay, let's say we have a column representation like the A1 through the A2 through the AN, and there is the vector like x1, x2 through the xn, and x1 plus 1, xn plus 1, right? In this case, what? The size of this matrix is m by n, and size of this vector is the m plus 1 by 1. So in this case, we can compute the multiplication of this one and this one, this one and this one, this one and this one. What about this one? There's no remaining vector, column vector here, so we cannot compute this one, right? So in this case, we cannot multiply this matrix A and B. So it means that when compute the n by n matrix A and n by 1 matrix B, these two values should be same. Okay, so this is a matrix equation. So for example, there are three vector v1, v2, v3 in the Rn space. Write the linear combination of the 3v1 minus 5v2 plus 7v3. This linear combination as a matrix times vector form. Okay, let's do that. Okay, we have a v1, v2, v3. Okay, let's make these three vector as a columns of the matrix A, right? So in this case, it will be the new matrix A. What is the size of this matrix A? Because the size of this column vector was the n by 1, and there are three columns, so the size of this matrix will be the n by 3, right? And there is the weight value. Please be careful to copy this sign signal as well. Okay, so these three values will make another vector x like this, right? So the size of this vector will be the 3'1. Okay, so in this case, this is a, this is x, so it will be the a times x. So what does that mean? The linear combination of the vectors can be represented in a a times x form. Okay. Okay, now the system of linear equation as a vector equation, like this one, involving the linear combination of vector. Okay. For example, let's say we have a linear system like the two equation with a three variable, right? Then what does it mean? What does it mean? Here we can represent ax. We want to represent this equation in a ax form, right? So then how can we do that? Let's say there is the 0 times x1, right? So it means that we can represent this first term is a x1 times 1, 0, right? Plus this term will be the x2 times 2, negative 5, something like this. So finally, this whole system will be represented like this. So this coefficient 1, 0, 2, 5, negative 1, 3, 4, 1 will be the column vector like this, and this will be the b, and this is the weight or coefficient of this linear this vector equation. Okay, then what does that mean? From this equation we can convert this notation like c1, c2, c3 times x1, x2, x3, something like this. So this is a vector notation, right? Right? With the vector v. If we define that this is a matrix A and this is a matrix X, then this notation will be represented like this. Okay, right? What does that mean? Okay, where are we now? Okay, we have a linear system. We have a linear system and we want to solve this linear system. we want to understand this linear system. But there are so many popular methods that solve the AX that defines in a AX equals B form. So what we want to do is to convert this linear equation in a AX equals B form, right? So it means that we can represent any kind of linear system in this form like this. So if we define this is a matrix A, this is a matrix B, it will be the AX equals B. So in this case, so AX equals B form is called the matrix equation. This is really important. Actually, AX equals B is the reason why we run the linear algebra in this course or the other graduate course. So from now on, we will talk about what is the AX equals B and what is the property of the AX equals B and how can you solve this AX equals B. Anyway, please remember this AX equals B is the matrix equation. Okay. Okay. So why this matrix is important? Because the solution of this linear system are here, right? Right. So it means that AX equals B, in AX equals B, the X vector will be the solution of this linear system, right? Then the solution of this linear system can be represented in a vector form that can be solved by some method in AX equals B. Okay, let's move on. Okay, there are one theorem. If matrix A is an m by m matrix with the column A1 through the AN and P is in the out N, the matrix equation AX equals B has a same solution set of the vector equation x1, A1, x2, A2 through the xn, and through the equals B. We already talked about this one, right? From here to here, right? Then which has the same solution as the system of linear equation whose augmented matrix is A1, A2, AN, B, something like this. So this is the exactly same solution with this one. Okay. So what I want to say is that this form, and this form has a same solution set. Okay. Here is one more theorem. Let's say matrix A is a m by m matrix. Then the following statements are logically equivalent. What does that mean? These four kinds of the statement should be all true or all false. So these four kinds of statement should be what? Should represent the same statement. Okay. Let's see. For each vector B in the Rm space, the equation Ax equals B has a solution. What does that mean? For arbitrary matrix A, if Ax equals B has a solution, then it is equivalent to the another statement. Let's see. Each B in the Rm is a linear combination of the columns of A. Right? What does that mean? If the vector B is a linear combination of the columns A, the equation Ax equals B has a solution. Inversely, if the equation Ax equals B has a solution, the vector B is a linear combination of the columns of A. Okay. Another statement here. The columns of the A span Rm. Okay. The last one is A has a pivot position in every row. What does that mean? We will prove this theorem from here, but let's think about that first. Okay, we have a matrix A that represents like this, right? And we have a vector B like B1 through the Pn. And what we want to do, find the matrix X like x1 through the xn, something like this. So what we discussed previously, we can represent any linear system in a ax equals b, right? So then we can find the solution of the ax equals b, right? If there, okay, let's write first. Right, like right. So what is that? x1 a1 through the x2 a2 plus xn an be like this. This one. Okay, same. So what does that mean? If there is the solution of the ax equals b here, there exists this weight to value here, and then this vector b can be represented in a linear combination of the a, like this. Second statement, right? It means that columns of a, like the a1, a2, an, span the every point in the Rm space, and it means that matrix A has a pivot position in every row. What does that mean? In the last lecture, if the matrix A has a pivot position, there exists a what? Solution. Okay? So it means that these four kinds of statements represent the same property of the linear system. Okay, let's prove here. Okay, statement A, B, C are logically equivalent, right? This one, right? So we will just prove that A statement A and T are true or not. Then if A and T are either true, so this whole A, B, C, D statement are all true, or if A and T are false, then the A, B, C, D are false. Okay, so first of all, okay, we have a matrix A like this. So first of all, to solve the system, we can represent the echelon form of the matrix A as a U. And then we can represent the augmented matrix of our system like the A, B, like this. Then we can reduce this augmented matrix like U, D with some arbitrary vector D. Okay? If the statement D here, A has a pivot position in every row, then each row of U contain a pivot position here. Okay? And there can be no pivot on the augmented matrix. What does that mean? Let's say there is vector matrix U and V. If this statement is true, there are every row has a pivot position, something like this. Then it means that there is no pivot position here, right? So in this case, in the last lecture, we know Ax equals B has a solution or consistent for any P. For any P. right? So it means that A is true. This one is true. Okay. So another case, if D is first, I mean, if there is no pivot positions here, let's say if there is no pivot position in the last row, then it will be the whole zero. Then vector D be the any vector with a 1 in the last entry, like blah 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 0 0 0 0 0 and 1, like this. Then in this case there is no solution, so this system is inconsistent system, because the from UD this system is inconsistent. We can say that A B system is also inconsistent. So in this case A is first, right? Because AX equals B has no solution, right? So this is the proof of this theorem. Okay. Okay. Let's move on to the compute AX. Compute A times X. Okay. Let's say matrix A is the 3 by 3 matrix like this, and vector X looks like this. Then how can we compute A times X? Actually, we already learned how to represent this, but in here we will talk about more systemical way to compute A times X. Okay. First of all, this is matrix A, this is vector X. Then what we want to do is we already know each column, let's say A1, A2, A3. Then we already know each element will be the weight of each column vector, A1, A2, A3, something like this. And then how can we compute this one? Just multiply on each element like this, like this, like this. You can do in yourself, right? And then we can just add this whole 3 entry like this, like this, like this, right? So from here we can see this row vector with this column vector, dot product of this one is this one, right? What about second one? This second row and this vector, the dot product of this one and this one is going to be this one. Finally, this one and this one, dot product of this one and this one will be going to like this. This is the row vector rule for computing A times X. What does it mean? The ith entry in the AX is the sum of the product of the corresponding entry from row I of A and vector X. What does that mean? Let's use the color. Yeah. This is the ith entry. Okay. Ith entry. In here, I is equal to 2, right? In this case, to compute this one, we need the ith row. It's 1, 5, 3, and x1, x2, x3. Okay, so that it will be negative x1 through plus 5x2 plus 3x3. So it's going to be this one. So to compute the ith row, ith entry in the A times X, we need the ith row times the vector X. Okay. So here's the general rule. Okay, we have a matrix A and we have a matrix X. Then output of the A times X will be the, okay, let's say this is the some row vector like this. Okay, and this is x1, x2, and in this case A1 time let's say just multiplication like this, x1 x like this. So this is a row vector rule for computing AX. Okay, so there is one more concept, is identity matrix. Identity matrix is really simple. Let's say I2 is just 1 1 0 0 and I3 is equal to 1 1 1 0 0 0 0 0. There are only 1 in the diagonal term and there are zeros in the non-diagonal term, like this. And the general formulation of the identity N, identity matrix N, is equal to like this. So why is important? If we multiply the identity matrix with a vector X, it's going to be vector itself for every vector in Rn. This is a very very desirable property when we compute some vector or matrix operation. Okay, there are last two concept or last property of the vector and matrix product A times X. Here is theorem. If A is the m by m matrix and U and V are vectors in Rn, and C is a scalar, then there are two kinds of property. Okay, so yeah, let's see first. The first one is A times U plus V is equal to U A times U plus A times V. Another one is A times CU is equal to C times AU. Actually, this property is really similar to the vector property, right? But there is a matrix notation. But this one is also can be easily proved by some vector and real number property. Okay. Here is a proof. Okay, how can we prove this? Okay, let's say matrix A is composed of the column vector A1, A2 through the AN, something like this, right? Then U is represent UN like this. V is represent V1 through the VN, looks like this. Then the right hand side will be the A1, A2 through the AN, right? With the vector U1, V1, U2, V2 through the UN plus VN, like this. Okay, so what do you want to do? U1 plus V1, this, because this is color value, times the column vector A, U plus V2, A2, no, UN plus VN, AN, like this, right? Then Then what else? Because this is a linear combination, so u1a1 plus u2a2 plus u3a3 plus u1 v1 a1 plus v2 a2 plus v3 a3, like this. Then it will be what? A times u plus a times v. So this is the proof right hand side, and this is the left hand side. So this is the proof of this system, right? To prove this one, okay, let's use the same definition like this. Okay, let's write the right hand side first. So a1, a2 through the an, right? Then what is that? Cu means cu1, cu2 through the cun, right? Right? Then cu1 times a1 vector, cu2 times a2 through the cun times an vector, something like this. So, and then what is that? What does that mean? cu1 a1 times something like this, cu2 a2 vector, like this, cu3 a3, something like this. So finally, cu1 a1 plus u2 a2 plus u3 a3, right? Then c is equal to be a vector u. Okay, so this is the right hand side and this is the left hand side, so this is the proof of the second property. Okay. Okay, so this is the end of the matrix and vector equation. What we have learned today? Okay, comparing to the last week, we learned the ax equals b. Ax equals the b representation. So from now on,